For our next talk, we have Alex Miller from Thermovant. He's going to talk about high temperature oscillating heat pipes for radiator management of fission power generation.
All right. Well, good morning, everyone. This is Alex Miller at Thermovant. I'm a lead engineer in our technology development group, and we're excited to share some work we've been doing on a SBIR program with NASA Glenn we're in phase 2. And my co-presenter here, who's probably going to be on mute, but here to swoop in if any of you have any challenging chemistry questions, Dr. Hilsenbeck. All right, so outline, we're going to go over the SBIR project overview in general, some related work that fed into this effort, our roadmap for radiator development, a trade study performed on the phase 1, and then a summary of the ongoing efforts on the phase 2, some analysis and design, breadboard manufacturing, some performance test results of those breadboards from the last 6 months, finally a summary. All right, so for context, we're operating this SBIR program under NASA Fission Power. The overall goal is to continue development of thin oscillating heat pipe radiator panels targeting approximately meter square scale by a couple millimeters thick to reject waste heat from FSP reactor systems at the intermediate temperatures required, mature the technology for implementation. We have a SBIR timeline here. We executed the phase 1, and now we're actually in Q5 of the phase 2 that wraps up next summer. So back to the phase 1, the actual NASA solicitation that we were, submitted a proposal for. The big thrust, or the big aim from NASA was to develop freeze-tolerant heat pipe radiators that can operate through a lunar day and night, so a wide range of sink temperatures. So our proposed solution, really the core of that phase 1 proposal was to develop intermediate temperature OHP radiators, quantify limits of operation, and better understand their performance. So to do that, we needed to demonstrate working fluid options in a temperature range that had before really not been explored in depth with oscillating heat pipes, and that's in the range, sort of above electronics cooling's applications, so 100 to 300 C. And then, need to demonstrate that those can be compatible with suitable envelope materials. We will elevate technology and manufacturing readiness levels through testing and manufacturing, efforts on these phase 1 and phase 2 SBIRs. All right, so the work that led into this was a phase 1 and phase 2 that ran 2018 and then wrapped up actually last year. And that was our first real push into larger scale radiators, but at lower temperatures. So again, aluminum based envelopes for applications up to 360 K, largely for management of silicon based payloads. So these were in general 2D spreading of point loads. You can see lower center image here was our final quote qual panel, the one that went through a mock qualification. So there's a mounting point in the middle for some mock payload that has some waste heat generation, and then the purpose of the OHP radiator is to essentially spread out that heat with very low spreading resistance. So we were able to demonstrate breadboards in the quarter to half meter square scale, where the essentially the gradient's very, very low, on the order of 2 degrees. So the rejection uniformity is, approximately isothermal. We were able to show thermal resistance, as low as 0.005 K per watt up to 600 watts in these products. We tilted them and didn't see any effects of gravitational orientation. Lastly, we did some demonstration of actually in the same vacuum braze construction where we generate the internal microchannels for the working fluid. We were able to, essentially in an adjacent plane or in the pockets between the channels, if the pitch is high enough, put in void space that's dedicated not for the working fluid but for phase change material. So you can charge an adjacent volume that's in intimate thermal communication with the OHP microchannels to essentially dampen transients with PCM, wax type materials. So quick roadmap where we are in radiator development. We had these phase 1 and phase 2s we just spoke about, where we matured aluminum radiators to run essentially up to about 100 degrees C. That's with ammonia working fluid. And the next step is to transition that to, actual commercial NASA DoD type satellites, where we had a NASA phase 3 on the Heather program, looking at applying these type of large area surfaces to outer mold line cooling of electric aircraft. Also looking at, moving to higher temperatures as required for fission power applications. So on that phase 1, we did a trade study, essentially looking at, how are we doing compared to what's been demonstrated? So ACT did some work demonstrating these tie water VCHPs with a carbon fin for fission surface power applications. And our trade study performed back on the phase 1 was looking as directly in apples to apples as we thought we could look at. And for the purpose of that trade study, we held the radiator temperatures, average rejection temperature, actually fixed with their reporting, and we're able to show, predicted that we could get, kind of significantly higher specific power and conversely lower areal density, and a lot of that comes out of having an improved interface, actually at the evaporator interface with the ultimate heat source for the radiator system, where we can put in a integrally brazed manifold for the PFL system. There's a low DT between the PFL working fluid and the OHP itself, and but this was driven by operation at around 100 C, and at the beginning of the phase 2, NASA lifted the temperature targets for us, so there was a pretty big switch for us between what was previously mature from a working fluid perspective, acetone, ethanols, and things that at 100 C have been demonstrated compatible with aluminum to the new target temperature. So here we have a compilation of the phase 2 sort of targets and requirements fed by the team at NASA Glenn. The big one being that they wanted to see 175 degrees, essentially at the interface, the OHP evaporator with the PFL loop, where that PFL is running on the cold side of a Stirling cycle for power generation. So there's a requirement to lift up to 175 C for the radiator panel, and then the rest of the targets are somewhat intuitive, low areal density, and then lastly, this bullet at the bottom, we pushed them, that team, pretty hard to quantify for us, and that was regarding the freeze tolerant specification. And so we're looking at essentially a min exposure temperature down to 50 K cycled 6 times, and that would be essentially before the reactor's up and running. So once the fission reactor is up and running, the part will not undergo freeze thaw cycles in operation, but perhaps there's a half dozen freeze thaw cycles prior to the system really up and running. So the nexus of the problem is finding OHP working fluids that are freeze tolerant down very cold. All working fluids that work at 175 are solid at 50 K, and additionally, we're really hoping at 175 to be able to use aluminum envelopes. Aluminum's sufficiently strong, obviously has high thermal conductivity and low density. So what working fluid compatible with aluminum works as a good OHP fluid at 175 and can survive some number of freeze thaw cycles in aluminum envelopes? So at the beginning of the phase 2, we conducted a trade study, and this was largely driven by our more commercial partners asking for these tables specifically so they could go do system level sort of trade studies. So the questions we're getting from industry are, what are the specific power and areal density of OHP radiators in this intermediate temperature regime from 150 to 300? And at the time, we had no experimental data to inform this directly. Essentially, we hadn't made any OHPs up in this temperature range. So we did some extrapolations from testing done at lower temperatures and the known thermophysical properties of a couple working fluids here. So hypothetically, we looked at aluminum, ethanol, and Thai water OHPs across this range, and looked at the sensitivity to specific power and areal density across temperature and with a transport distance. One takeaway from this is that a primary output of the phase 2 itself is an updated version of these charts that has realistic error bars and just much higher confidence. Validated and anchored by experimental data. So also early in the phase 2, before we produced any hardware, we took the manufacturing designs that were about to be released and pulled them into a finite element environment. Essentially, we took our first pass at predicting what the performance was going to be prior to that testing. And similar to the trade curves on the previous slide, we had to take a stab at channel characterization without having highly relevant empirical data to guide it. So the channel characterization was based on extrapolations from sort of traditional fluids, but at lower temperatures, closer to 100 C than these at 175, as well as not having meter scale data at those temperatures either. So the gist is we decided to go with a 6-inch wide by 4-inch long breadboard geometry. The input evaporator interface is a 3-inch long in the transport direction by full width of the part. We perform these sims with a constant flux input boundary instead of sort of like a PFL analog, more like a isothermal boundary condition. Applied a high emissivity sink at that 50K, the min sink specified for the lunar condition. And so here's a general output of these sims showing sensitivity to whether the radiators are functioning, the physical rejection surface is a single side of the oscillating heat pipe or both. And if we have a low number of internal microchannels or a high number embedded in the same exterior geometry. So the gist is we predicted sort of 17 to 59 watts per K for the two-sided rejection as a function of channel count. And then during testing to follow, it's come out at 21 to 36. We'll look at those in the next couple slides. And those breadboards sort of had low to moderate channel counts, sort of relative to the ones that were simulated. So we had, decent agreement in terms of the extrapolations performed prior to testing. And there's a note here that this kind of large sensitivity to channel count in the simulations is due to the, when you go to higher channel count, you physically have higher evaporator channel area. The actual, wetted area in the evaporator scales linearly with the number of channels, as we weren't playing with the channel geometry. So when we assign convective film coefficient there in the simulation environment, the higher area just proportionally drives lower flux and lower DT. So hence that rolling into the wide performance prediction. All right, so with the performance predictions in hand, we moved forward with manufacturing. We had this fixed 6x44 envelope geometry, a couple through holes for heater attachment, and then actually went with 8 different internal channel geometries. These resulted in a thickness ranging from 2 to 3.5 millimeters, and the areal density of the parts between 2 and 4 kilograms per square meter. On the right, you can see up on our rack in the lab what those parts look like after so stage 1 machining is where we machine the channel body and the lid. Then we vacuum braze those together and then cut out the final geometry. So these parts have gone through an initial characterization, essentially looking at fluid performance in what we're calling the open air test bed, which is obviously just sitting out in our laboratory environment, and a little bit different than operating on the lunar surface. But it turns out that we can do some really high throughput testing versus having to try to operate these in a large TVAC chamber. We don't actually have a large enough TVAC chamber at Thermavant to handle this 44-inch long part. And at a 165-degree, essentially average rejection surface, the flux is actually relatively close to what you get in a pure radiative environment with that cold sink. So we have an ambient, 20C sink in the lab, and the rejection flux is about 15% higher than we'd see, in the application environment at the same temperature due to that free convection off the surfaces. So we have a TC map on the right, fairly densely instrumented, so we really know what's going on at the heater block, at the interface between the heater block and the UHP, and then on both the top and bottom rejection surfaces. For the analysis equations, in terms of how do we get from the raw data collected to the metrics that we throw up in the plots, I'll go through these quickly. We look at the input power, which is the measured, I squared R electrical power in the cartridge heaters, minus these losses. These are, this is, heat that comes directly off the heater block and does not get, essentially absorbed and transported by the OHP itself. So we quantify these with tear tests, essentially some specific testing to know how well insulated that heater block is from the ambient environment. The rejection power is calculated directly from the temperature map on the rejection surfaces, where we use standard, undergrad equations for natural convection and radiation. So we know the surface temp, so we can calculate what the rejection power should be. And then comparing the input power to the rejection power is a good energy balance to know, is there anything happening that we're not really capturing? Are the losses incorrectly captured? Is the emissivity of the surface not close to what we think it is, etc. Next, we need to actually, yes.
We got about 3 to 4 minutes left.
Wow, that goes fast. All right.
Yep.
Great. So the other metrics of interest are the spatial gradient across the part, and then the quotient. How much power are you transporting per degree of spatial gradient incurred to the thermal conductance? So I'm glad I put the summary up front here. We've tested a handful of these breadboards, and the results are summarized on this slide. That one of those breadboards that had a 3.1 kilogram per square meter areal density is showing a 36 watts per K conductance at the specified target operating point. That's 175 degree evaporator temperature. This is 40 times the thermal conductance of the mass equivalent part, the aluminum control radiator. So we test the exact same geometry, mass equivalent solid aluminum, no working fluid, and we're seeing a 40x improvement in the thermal conductance with the working fluid and the OHP operation. So the working fluid we're using is, we're holding it a little bit close to us right now. I share with our NASA team, but defeatured it a little bit for this presentation. It's a alcohol binary mixture. The tests are conducted with high emissivity, and the data shown here is after fluid optimization. So we've varied the liquid fill fraction, looking for the highest conductance and stability as a function of that liquid fill fraction, and then applauded those results here. So one breadboard, our favorite, is shown in the top series, best performer to date. We've demonstrated 10 degrees of margin, operating it up to 185 degree evaporator, not pushing that too much higher because you start running into the point where the yield strength of the aluminum envelope falls off. We characterized another breadboard that had smaller channels, it had lower conductance, and then one with aggressively low channel count, and we ran into a hot limit at this 185 degree point. So the gist here is shown on the upper right is this control test. We step the solid aluminum control through a variety of temperatures, look at the power that it's able to reject and the gradient incurred across it. And then the lower plot is that exact same aluminum structure charged with working fluid, and we see the large improvement in uniformity and thermal conductance. So One other takeaway is that the OHP limits charts are actually predicting startup, so that's the onset of nucleate boiling, very close to the experimental observation here shown blown up in the inset. So that's you can compare the startup condition here where the DT across the part starts to drop rapidly to the red line in the limits chart. So we have good agreement in where we start up with large margin to the operating points. There's no question about risk being close to startup. But we're also predicting margin to vapor inertia limit, the effective hard-hot limit, and we've not encountered that in the testing with this part to date. Those that are more familiar with the OHP limits of operation as developed by Drillman and Smoot see that we have essentially no margin to the swept length limit, and we've not encountered it in testing. So the asterisk here is that we've seen this before, that the swept length limit didn't appear to manifest for OHP spreaders with full backside cooling, where there's ability for heat to be rejected directly opposite the input surface. So that swept length limit for this configuration, heating and cooling map, is still somewhat in development. Tested part with the small channels. You can actually see the spatial gradient in the IR, and this is due to higher viscous losses due to pumping that working fluid through a small hydraulic diameter channel. So we see the proportionally lower conductance due to that incurred viscous loss. That test we tilted DZ equals L over 6, similar to testing vertical on the moon, and there was no change in performance. So in summary, we've demonstrated for the first time high performance meter scale aluminum OHPs relevant for rejection from Stirling cycles in the 150 to 185 C range, seeing performance 40 times that on a mass equivalent basis to solid aluminum radiators. The first candidate working fluid has shown initial compatibility with these aluminum breadboards throughout the test campaign, but long-term compatibility is still a primary risk. We need to do some high-fidelity life testing before these are ready for insertion in a long service life mission. We started making OHP limit charts for the first time for mixtures, working with binary mixtures of fluids versus the pure fluids. They seem to predict startup and the hot limits reasonably well without any tuning parameters. And the rest of our efforts on the next 3 quarters are to continue development of novel freeze-tolerant working fluids in this 200 to 350 range, and pursuing a variety of post-phase 2 opportunities. I want to say thanks to the Thermobond team and Greta and Jim Sanzi at Glenn for we have monthly tag ups, and they've been really supportive in this effort.